org. So with that, it's my pleasure to introduce today's speaker, Mark Millard. Mark will be presenting on Great Scott, a homebrewed recipe for regional trend-based log normalization using various examples from the Rocky Mountain basins. Mark is a consulting geologist and a free agent with Novel Stone Geologic Consulting. He has 15 years of experience in the Williston, Powder, and nearly every other basin in the Rockies in Texas. He has worked a multitude of roles from frontier exploration through field development for private PE-backed companies and large public companies, including Pioneer, SM, and Rockies Resources. Mark is the author of 29 papers and/or technical presentations. Mark currently serves on the Geologic Advisory Board for BYU Idaho and was previously the president of the Montana Geologic Society. He received the A.I. Leverson Award for the RMS AAPG, the Frank Waltzke Memorial Award from the AAPG Energy and Mineral Division in 2014. He got his master's from Baylor and his undergrad from BYU Idaho. His interests outside of geology include building mandolins, guitars, violins, and playing bluegrass music. And we can already kind of see from the video here. So with that, please join me in welcoming Mark Millard.
Thank you, everybody. And Dan and Debbie, I will not have my chat turned on. So if anyone has any issues, you're going to have to just jump in and talk to me there. I want to thank everyone for being here. And I want to start out with a short little story. Yesterday, for anyone that sat in on the Denver Data Drivers webinar, I highly recommend getting in there. It's like Geoscientist meets the movie Hackers. It's pretty cool. But before it began, a couple people were chatting, and I got in there. I logged on, and someone said, "Oh, what's the RMAG talk tomorrow?" And someone who will remain nameless said, "Well, it's log normalization." And right then, my heart sunk. But he followed it up with, "But it's probably really important for us to learn." So, I agree completely with that. When you hear log normalization, it's kind of a downer. But it is very important, and I'm going to show you a geologically honest way to do log normalization. And also, I'm going to add in some music and trivia to try and liven this up a little. So with that, we'll go ahead and get started. And I want to talk first about the relationship between geology and music, and more specifically, log normalization and guitars. Now, this here is a tenor guitar. It's one that I built a few years back. And they're a little different than normal guitars. This one only has 4 strings. It can go up to 8 if you want. But with a guitar, one of the most important things you have to learn how to do as a musician, give me 1 second here. Is learn how to use a PowerPoint. One of the most important things you have to learn how to do as a musician is tune your instrument correctly. And when you tune an instrument, essentially what you do is you have 4 different strings on this one, or 6 strings on a real guitar, and you adjust the pitch of the strings until they form a desired arrangement, so they sound good together. Now I'm going to show you this guitar, and we have this image here of 2 tones that are out of tune and 1 that has them in tune, and you'll quickly realize this guitar is out of tune. So what you have to do is you have to normalize, or I guess correct term is tune the strings to get them in sync with each other. So those 2 sound good together. Let me go to my 3rd one here. And to tune them, what you do is you turn the little tuning pegs up here to adjust the tension of the strings. So you go ahead and you find out which string is the one that's the odd one out. And you just tighten it or loosen it until it gets the correct pitch. And then when you play, everything plays in tune. Now, strings can go out of tune for a number of different reasons. It can be due to changes in humidity. This is a big wooden box, so of course it absorbs water and changes its volume. The strings can also wear out, much like you see with wireline logs. You could also have issues with a poorly constructed bridge or nut. And also these little tuning pegs up here can break with time. Or break, I guess, kind of wear out, if you will. So, like I said, these oftentimes need to be tuned to keep them functioning correctly. Likewise, when we look at logs out in the field, they also need to be tuned correctly to work in sync with each other. And that's where we have log normalization. It's essentially an attempt to non-logic variability in log data. And there are many common causes of log errors. I've got a few of them listed here, like miscalibration, differing vendors, changes in tool design. The differing vendors one is an interesting one because back in, I think it was 2009, when we were working the Eagle Ford at Pioneer Natural Resources, we did a test. It was very early on in the Eagle Ford play, and we drilled a pilot hole, we cored it, and then we somehow convinced 3 logging companies to run their tools in the hole for free, so we could compare the 3. We went ahead and did this, logged the well 3 different times, and then we compared the results. And 2 of the companies had very, very similar log results, whereas one of them was actually pretty significantly different. Now this is interesting because this is all in the same well bore. The temperature and other conditions might have changed a little bit, but not enough to cause that much of a difference. This shows how different tools read differently, and it shows why you do sometimes need log normalization. Another big issue is digitization errors. As you all know, a lot of the logs that we use are poor photocopies from logs that were collected 30 years ago and then photocopied 8 times. And then we also have issues with environmental corrections that are improperly done or not done at all. And I'm going to show you a few examples of why we really need log porosity, or why we need log normalization. I'm sorry, we all need log porosity, but why we need log normalization. This is an example from the Sussex Formation in Powder River Basin. And these 3 wells that you see here are all within walking distance of each other. And what I've got is gamma ray, resistivity. I've got a total porosity in black, and then a calculated effective porosity in blue. And then I've got water saturation here on the last one. And then I've gone ahead and just flagged what I've considered pay. And what's interesting is you'll notice the well in the middle has the most porosity, has the most pay, the thickest section. But what I've done is I've run a red line through here that was my shale porosity baseline. And what I essentially did was kind of find, ignoring some changes in lithology or washout, I went ahead and found kind of the 0 line. It wasn't even a 0 line, it was just a baseline for your shale porosity. And you can see it runs right through here. We look at this well and it kind of runs right through there also. But if we look at the well in the middle, you'll notice our black curve, our total porosity, seems to be shifted to the left. You see that through the entire shale section, and you actually see it in the section above. This is a pretty obvious example, but right here, this log needs to be normalized. It needs to be corrected. Now, assuming we didn't normalize it and we just saw it as a beautiful bullseye and we want to drill that well, if you run the petrophysics based on this simple model that I built here, apologies, I'm using an apple, which is I'm just going to leave that one out there, if you will, for a second. I am not a big Apple fan, but it's okay. So if you run the petrophysics on the raw logs, you come out with about 60 feet of net pay, and you get about 8.8 million barrels of oil in place per 640. So it's a decent well. It will make a decent well. But when you go ahead and normalize that log and correct it and rerun the petrophysics, you're down to 4.2 million barrels of oil in place. Once you correct this porosity, it's going to look a lot more like the wells on either end of it. So as you can see here, an uncorrected row B resulted in an overestimation of 4.6 million barrels of imaginary oil in place. Now, that can be pretty significant. Now let's assume that your porosity was correct, but you had an issue with your gamma ray. Your gamma ray needed to be adjusted, needed to be normalized. If we only adjusted this gamma ray by 10 API, that would add or subtract almost 1 million barrels of imaginary oil in place. So it could be pretty significant. Of course, this is going to vary depending on how sensitive your petrophysical model is, but in this simple example here, you can see it's pretty significant. So there is a strategy to accommodate for this, and it's log normalization. What I'm showing here is basically the most commonly used normalization method in industry today, and it's a field average. And we're going to do it with a 1-point normalization using mechanical shift. I've got the simple equation, as you can see here, blue plus green minus red. And to get these values, first for the red, we do the well average. It could be a P90, P50, P10, whatever you want, but the well average for your normalization interval. So the average gamma ray of the shale here comes out to be 95 API. So you've got the value right there. Then we go ahead and we calculate that well average for all of our wells in our field. And then we basically just average those together and we come up with 100 API. And then we just calculate our gamma ray value at each depth. It's a very simple process. Most geological software can do it. Yesterday I was challenged in the data, Denver data drivers group to produce, and I was almost successful. I got the code to say hello world, and that was it. I couldn't get past that step. But again, field average is the most commonly used method because there are a lot of pros to it. It's easy to calculate. It takes multiple wells in consideration, so there's strength in numbers. But a few of the cons are that, first of all, erroneous wells are included in the field average. And also it works locally, like on this small scale, but it does not capture regional geologic variations. And that's why we're talking about trend-based log normalization that I'm going to show you later on in this talk. So I'm going to show you even more geology and music. Some of you may have noticed when I played this guitar, I had this little clamp on here. This is called a capo. And what it essentially does is my guitar, the scale length is about 21 inches long, but when I put this capo on, I'm only dealing with about 14 inches of scale to work with. My AOI is really small in this area. My field is really small. When I take that capo off, it changes my scale length. Now I've got a much longer scale length. It affects my string angle as we're coming off the bridge. It affects the tension, and it also affects the tuning. So if you remember, I did tune this correctly, but now that I removed the capo, let's see what it sounds like. You know, it sounds decent, but it's a little bit off. The string tensions are a little bit off. And so oftentimes when you take off the capo and you change your AOI, your scale length, you do need to make minor adjustments to your tuning. You need to renormalize these logs with a longer scale length. Let's see, that's probably good there. That's good. Now likewise, when we're working with the field average, when we're normalizing log data, you've normalized your data, everything's good, but then you increase your AOI, your field average changes for your log normalization. And there are many mechanical reasons as to why this occurs, but there's also a geologic reason. And the easiest way to think about it is oftentimes we're normalizing using a marine shale, a gray shale. And you know, they're pretty consistent across the basin, but there are very slight changes that you see from going from distal to proximal. And here's a very non-geologic example. Let's say we had a log here closer to shore and deeper to shore. Your gamma ray character of your normalization interval is going to change across a regional scale. Notice I only changed a few API, so most people wouldn't notice it when they're watching the logs. So I'm going to show you a real life example of this change that we see when we use a field average. This map down here, these are townships. So we have 17 townships here, and I have a smooth map of my P90 for my gamma ray for the shale that sits above the Sussex right here. 105 API down to 100 API. If we go ahead and normalize our logs, let's see, okay. Go ahead and normalize our logs for that 17 township AOI. Our average gamma ray, our P90, comes out to be about 102. Oh, you saw a little cheat sheet there. 102, because we have 100 and 105 down here. And we come out with about 4.2 million barrels of oil in place per 640. Yeah, that's great. But let's say you decide to expand your area of interest. Instead of looking at 17 townships, you're looking at the entire basin, as you can see here. And now we're looking at about 80 townships. Now, if you were to go ahead and find your field average, as you can see, the gamma ray is changing regionally across the area. Our field average is now 97. So it went from 102 down to 97 just by changing our AOI. When you run the petrophysics on that and the oil in place calculations, we now come out to 4.6 million barrels of oil in place. So as you can see, increasing the size of the AOI resulted in a variation of 0.4 million barrels of imaginary oil in place. So it can be pretty significant. Now there is a solution for this, and that's what I'm going to show you today, which is regional trend-based log normalization. But I'm going to show you one more, even scarier example of using a field average for large AOIs. This chart on the left, you all have probably seen it before. I've got porosity on the x-axis and depth on the y-axis. And all it's showing basically is that at surface, our porosity of our shale is very high, 50 to 60%. But as we bury that shale, it's going to compact, as you can see here. Now, if we look at this Sussex map on the right, let's say we're normalizing our porosity logs in this area. I have one well that's up here that's about 7,000 feet, and the porosity is 15% in the shale. That same shale, when you bury it down to 10,000 feet, my porosity has decreased down to 10%. Now I ask you, if you're going to use a field average to normalize this area, what value do you use? 10, it's going to incorrectly estimate the wells up here, and vice versa. If you use a number in between, that field average will work great in this intermediate depth, but it will begin to fall apart in the deeper and the shallower depths. So what we need is a normalization method that works in a regional trending way, and that's what I'm going to show you right now. That method is not a new method. In fact, it came out when I was basically 1 year old, and it's called a regional trend surface analysis. And it's actually pretty simple. I'm going to show you the workflow so you can do this on your own. I prefer to do it in geographics, but you can do it in Petra. You could probably even do it in Python if you want to put forth the effort. We're going to use the same 1-point normalization with a mechanical shift, so the same equation that we used before, but the big difference is this green variable is changing. It's our variable field average. So just like we did before, we collect our well average, which was 95 API. We do that for all of our wells in our field area, and then we go ahead and contour those and smooth that contour map. So now our values go from 100 down to 98 down to 96. And now our variable field average comes from wherever we're sitting on this map. So if we're down here, it's going to be 96. If it's up here, we're going to be at 100. And this, in my opinion, now I think back about this, I gave this talk at last year's AAPG, and I believe this was the point where I started to tear up and cry. So I'm going to hold on strong this time. But in my opinion, best honors geology. It assumes that the log character of your normalization interval, for example, your marine shale, varies regionally, and it accommodates for that. So here's the workflow basically, and if you email me after the presentation, I can send you this PowerPoint, so you don't have to take all the notes right now. But this is the workflow that we've come up with to do this with modern mapping software. And so we start out by defining our zone of interest and our zone to normalize. We're going to work again with the Sussex formation, as you can see through here. And what you want to do first is find a zone that's near your zone of interest. And in this example, we're going to use this 50 feet of shale just directly above your Sussex. And you want it to be as geologically consistent as possible. If you're using like a P90, you want something like a marine shale. If you're doing something cleaner, I like to use like a tight limestone. But there are a few things you have to take into consideration. You have to think of log coverage. Many times you'll look at logs, and especially in the powder, and they'll stop logging, right 150 feet above the zone of interest, or they'll stop early, as you can see down in this example down here. So you have to find a zone that has good log coverage, and you also have to take into consideration casing, because that's going to mess up your well results or your calculations. So there's my zone of interest. Here's my potential normalization zones, and in this case, I'm going to use this zone just above our zone of interest. Once you've defined your zone to normalize, hold on 1 second here. We're going to define a zone. We're going to define a statistic. Go back here. Here we go. We're going to define a statistic that makes sense for log normalization. In this case, like I said, we're using a marine shale, as you can see here. So you could do a min, a max, a P50, a P90, a P10, an average. In general, for marine shales, I like to use like a P90-ish. And just for reference, I've got the value you would get from a P90 versus a well average, and you can kind of see where they fit along here. Here's our P90 just hitting right along here. And like I said, these statistics are specific to each and every prospect that you're working with. So, it's not a one size fits all when doing this. Once we've defined our zone of interest, we're going to calculate those statistics into a zone using our mapping software. For example, in geographics, we have Zone Manager, and we can go ahead and calculate the P90 for that zone into each well. As you can see, the data is listed here. After that, we get to the fun part, and that's where we start making maps. And we start out by making a map of the gamma ray of the P90, and you can see that map here. There's a couple interesting things that come out when you look at this map. First of all, you'll probably notice all of the bullseyes. Now, the contour interval on this map is about 5 API. So you can see some pretty significant bullseyes up and down the map. In fact, if we look at our statistics, look at our min and max, we have a min of 6 and a max of 170. That's, again, for this shale interval. That is not acceptable when doing petrophysics. That will blow everything out of the water. Also, if you look at the cross-section down below, it's oftentimes difficult to recognize normalization issues when you're looking at your sand. But if you look at the shales above and color them correctly, you can see the obvious issues. Here I'm looking for a nice consistent purple, but I get these greens that jump in here from time to time. So you can see the need for log normalization. And if you don't correct these now, they'll propagate through all of your petrophysical calculations. So after you've made this map, I like to take a screenshot of it and make a copy of it. And then we're going to start working with the copy of this map. Now what we're going to do with this copy is we're basically going to clean it up. We're going to try and remove as much of the erroneous data as we can. And this is where you put on your interpreter hat. And there are a couple ways to do this. You can do it manually, well by just checking each one of these and deleting them. And it's actually pretty fun to draw cross sections through here, and you'll see where all the errors are. Or you can do it automatically using a histogram. For example, again, I've got a min and max of 6 and 170. And here's my histogram. I go ahead and shrink that histogram, and I'm down to 80 and 115. So it's a lot tighter data set. Now, we don't need to remove all of the erroneous data in here. And you want to try and preserve regional trends. As you notice, it's getting hotter down in the southeast and kind of a little bit cooler up here. But remove as much as you can, and then we're going to go ahead and smooth this map. So now we're going to create a set of trend filter grids. We're basically going to smooth it. Again, in geographics or Petra, you can do this pretty easily. All I'm going to do here is change my feature filter diameter. So here I've got a 10,000 foot feature filter diameter. You can see the size of it. And I apply a filter to smooth this grid. We want to make it as smooth as possible. So this one's kind of too variable. This one's a little bit better. We're getting better. We're up to 30,000 feet. Still getting a little bit better. 40,000, it's starting to look better. 50,000 actually looks pretty good. You've removed all the bullseyes. You have a nice gradual climb from 95 API up to 105 down to the southeast. But again, it's a gentle climb. You know, if we keep going, go up to 100, it gets, you know, a little bit too smooth. So I think that the 50,000 foot is probably the correct number that we want to work with. So we'll go ahead and stop where we are with this map and save this map as it is. And just for reference, you can see there's a slight regional increase in gamma ray as we move towards the southeast. And here's all the different grids just for your reference. This is the one I ended up with. You won't always use 50,000 feet. It will vary depending on the data that you have, the data density that you have, and even the data quality. So you'll just have to kind of play this one and put on your interpreter hat to make it work. Once you've made this grid, we're going to go ahead and sample this grid back to all of our wells. Again, you know, through geographics or Petra, it's a pretty simple process where it essentially takes the value of the grid at each well and populates that back into the zone manager for the well. And now once we've done this, we're ready to finish up the log normalization. And this is where we return to our origins and we return to our canned normalization equation. Now it's gonna be a little bit different. I'm gonna show you where these green and red variables come from. The green variable, the variable field average, actually comes from our trended surface, and then our well average comes from our raw data. So now when we do this normalization, it's essentially comparing our trended surface to our raw data on a regional scale. So I'm going to show you two examples really quickly, two wells in the basin. Well A is up here in the northwest. And if you remember, if we just did a small little field average of this area, our field average would be about 95. Well, using the same method, we end up with 95. Come down here to the south, and our field average is more on the line of 100 API. So you can see how this normalization method would allow for you to do normalization over a regional scale while still being geologically honest. So of course the proof is in the pudding, so we're going to look at a few of the results here. And I've got a couple cross sections. This first one goes, it's the raw data, and it's riddled with noise. What I want you to focus on is the shales above and below. They should be relatively consistent color. But you can see there's a number of greens and purples bouncing back and forth. When we use a simple field average, it's much cleaner. We get about a 70% solution. But what's interesting is you'll notice these two wells in the cross section. This well here on the left that's circled, it went from green to more purple, whereas the one on the right went from purple to more green. So it normalized, but if you remember, our field average was somewhere in between these two values, and so overcompensated on one and undercompensated on the other. Finally, when we look at a trend-based method or analysis, you can see our shales are a lot more consistent throughout the entire cross-section. So if you hold on 1 second here. All right, so now we're going to pause for a minute. We're going to have a little intermission here and take a non-mandatory actually, Kahoot quiz. So if everyone can get on your phones again, log on to kahoot.it. Hopefully you already did it. And go ahead and put in this game pin number here, right here. I'm going to go ahead and change my screen here.
Hey, Mark, you might want to go back to that pin just for a second.
Yeah, I am. I'm going to switch to the other screen that has it. Let me pull it up right here. Here we go. So this should be it. So we've got 43 players. We'll give you another minute to get logged in. And like I said, time is of the essence when doing this quiz. The faster you answer, the higher points you get. And also, you'll look on your phone, and there will be little boxes that you'll have to click. You'll have to read the question on the screen, and then click the button here on the phone. We'll allow a few more people. We got 50 competitors right now, 51, 53. Give you about 20 more seconds to get in here. All right, we almost there? 59, all right, we got a couple more seconds and then we'll go ahead and get started. Ooh, we're up to 60, all right. So I hope you guys were paying attention. These are kind of tricky questions. I almost passed, so I'm hoping you guys can do a lot better than I did. Go about 10 more seconds. All right, if you're in, you're in. If not, you're going to miss the first question, but don't worry because everyone will probably miss it anyways. We got check the chat really quickly. Yes, as Debbie said, you have to enter your nickname afterwards. All right, we'll go ahead and get started. Here we go. Ready? And it's starting now, so read it off your screen. So number one, which of these is not a common cause of log error? Go ahead and pick on your phone, pick the correct answer here. Oh, the answers are coming in. You got about 10 seconds left. 40 answers. We've got almost everyone in there. And I think most of you should get this one correctly. The correct answer, yes, 49 of you got it right. It is changes in intrinsic permeability. Good, all right. So let's see who is in the lead now. Chris is leading the scoreboard here. Good to go, and BD's right behind you. All right, let's see what's next. In the Sussex normalization example, a gamma ray correction of 10 API would add or subtract how much imaginary oil in place? 0.5, 1.5, 1, or 2 million barrels of oil in place. And I want to give a shout out to Chantel for helping me get all this set up. If you join the trivia night, she's a much better hostess than I am, host or hostess. So definitely join in. What's the answer going to be? It was 1 million barrels of oil in place. Exactly. Let's see where the leaderboard is. If Chris still at the top, ooh, Matt is pulling up. There we go with 1,900 points. Third, in Back to the Future Part 2, what does Doc pack into a suitcase in case they don't have it in the future? Coffee, cotton underwear, a gun, or a radiation suit? What's it gonna be? And I hope you guys would pack the same thing if you were going in the future. It is cotton underwear. That was a tough one there. You never know. And the leaderboard now, Matt is still in the lead. He's holding on strong with BD right behind him. 4 of 6. Why does field average not work well for porosity log normalization? A, it does work well. Porosity is not measured directly from waterline logs. Or C or D. Got 10 answers. We got about 10 seconds left. 3 seconds left. 2, 1. 37% shale porosity decreases with increasing burial. That's correct. That one's kind of, I worded it. I didn't word it very well, so that was a tough one to get. But Matt has dropped off the leaderboard. I'm sorry, Matt. I apologize. BD, well done. 5 of 6. In Back to the Future Part 2, which political figure sells Marty a Pepsi Perfect in the Cafe 80s? Trick question. Michael Jackson, Jimmy Carter, Richard Nixon, or Ayatollah? All right, well, 1 second left, and the correct answer was not Michael Jackson. It was Ayatollah. Told you it was a little trick question. Now, I actually thought it was Michael Jackson, too, when I first found this quiz. Chris is still hanging on. Or, I'm sorry, BD is, not Chris. I apologize. Regional trend-based normalization requires more advanced math than one-point normalization using mechanical shift. True or false? This might be a little subjective, I guess, but I think most people should get this correct. 7 seconds left. This is for the win right here. Let's see if BD can keep in there, or if Chris can come back, and Matt. Ooh, it was. You know what? I apologize. The answer should have been true. Regional trend requires more advanced math than one-point log normalization. Oh man, I biffed it. I screwed it up. That last one should have been correct. But regardless, we're gonna give 3rd place to Ryan, 2nd place to Dan, and 1st place to, drum roll, Eric. Good job, Eric. So go ahead and why don't you maybe email Debbie after we're done with this. I apologize on the last question there. That's why you really need Chantel to be the host for these trivia nights. She does a really good job, and I would recommend joining in. We only have a couple more slides to talk about, and then we're going to finish up with something else. You may have noticed a lot of the, now I'm going to get a lot of a true lottery. Okay, yeah, June 18th. So there you go, sign in for trivia night. Now you may have noticed most of the questions were about Back to the Future Part 2. One of my favorite movies, because when I was about 9 years old, I actually got to go see the world premiere of it and meet Biff, of all people. So it was pretty cool. So a couple more things we're going to talk about with log normalization. I want to show you a few more examples in the Rockies. As you may have noticed, the Sussex example that I gave is very simple, very straightforward. And oftentimes we're dealing with more complex environments like the Permian or the Williston Basin or Uinta. So I want to show a few examples. First in the Williston, where we have an area that's predominantly carbonates. We don't see a lot of regionally consistent shale packages. So there are a number of different ways to combat this. The way that I have done it in the past is using a 2-point normalization with a clean carbonate and a shale. So for the clean carbonate, I like to use the Nisku or the lodgepole. If you use the lodgepole, you want to skip the false Bakken and go above that. And then for the shale, I often like to use kind of that shale that sits below the first bench of the Three Forks. And what I've got here are just the 2 maps showing you what my P10 and my P90 raw data look like. And you'll notice kind of a regional trend of hotter down here and cooler up here, hotter and cooler. But you'll also notice a number of bullseyes that are consistent on both maps. Now, the fact that we're seeing the bullseye above our Bakken and below our Bakken would suggest that these logs do need log normalization. So when you normalize them, you end up with something much smoother. This is the trend surface that we're using here. Now, when we look at the Uinta Basin, this one's even more complex. I've got this cross-section up here from, I believe, the gentleman at Newfield in 2014. And one of the challenges is we go from kind of alluvial plain environment, this is Lake Uinta, to kind of deep lake environment to the north. And there are no real consistent marine shales or tight limes that extend across the basin. And so I did a slightly different approach on this one in the past. I like to use like a 1,500 foot thick interval, and I apply a resistivity cutoff, so it ignores all of my sands, and then it also potentially ignores your really hot shales. And then I just look for a baseline along that 1,500 feet of the shales along that 1,500 feet. And when you do this and you do the regional trend-based analysis, you will see a definite change from the southern part of the basin up to the northern part where it's primarily deep lake, and then you start getting the alluvial sediments even above that. So a couple final considerations. First of all, log normalization is not 100% solution. As we found out yesterday in the data drivers talk, it's not really that fun, but it is definitely necessary. And it's not meant to correct logs, but it's really meant to remove the influence of non-geologic factors. And there are many different methods for many different situations, so you have to choose your weapon correctly. But in my opinion, regional trend-based log normalization is the most geologically honest method of log normalization. But you must remember this is an interpretation which affects every other calculation down the line. And so if you do it incorrectly or not at all, it can have significant implications. So really there's no pressure. Now I want to leave you all with a simple way to remember to normalize your logs. Debbie, if you could go ahead and take everyone off of mute. So everyone could come off of mute here for a second. I hope you can still hear me. All right, we got some people in there. Let me hear you just shout one time. Everybody shout just once.
Yeah.
All right. That is some serious. That sounds like 8 o'clock in my neighborhood, all the howling. So I grew up in the 80s. And so a thing that I heard all the time was this slogan from Folgers, and you guys probably know it. And it goes like this. Best part of waking up, Folgers in your cup. Okay? So we're going to take that song and we're going to normalize that song. And it goes like this. When your logs are all corrupt, normalize them up. I'm going to do it again. Then I want you to join in on the third time. When your logs are all corrupt, normalize them up. Here we go, ready? Everyone together. When your logs are all corrupt, normalize them up. One more time. When your logs are all corrupt, normalize them up. Wow, that was amazing. Amazingly awesome and questionable at the same time. I want to thank everyone for, especially for singing along.
Folgers commercial version of log normalization.
Yeah, all of your spouses or significant others or children are now wondering what in the world just happened. So welcome to my world. Debbie, you could go ahead and mute everyone now if you want.
Oh, Mark, I think you got muted again.
Consulting services. What's up, Daniel?
Oh, you were just muted for a second there. Go ahead and.
Oh. Okay, hold on. Am I
You're
still
good,
muted?
You're good now.
All right. As I was saying, if you want to contact me, if you want a copy of this talk or have any specific questions with log normalization, with trend-based log normalization, you kind of just have to work through it to figure out the little kinks to get it right. So go ahead and email me or connect with me on LinkedIn. You can also find my consulting services with my new consulting website here. Go ahead and check that out. If you have any other questions, let me know. I'm going to turn the time over to Dan now so we can answer any questions that anyone has here during the webcast.
Well, Mark, I want to say thank you so much. As always, wonderful talk, wonderful presenter. I'd like everybody to please start to use the chat pod to submit any questions, and I will be happy to read them back to Mark and facilitate here. We have about 10 minutes for questions before we end at 1. Mark, why don't I go ahead and kick it off? I have a question for you, which is when you started to use the filter feature and you went to 50,000 feet,
yes.
why would you want to go so smooth? It seems like even in the 10,000 or 20,000 foot, doesn't that still incorporate some of the, let's say, smaller, more localized changes that may be occurring? So wouldn't you want something like that?
Yes, yeah. I mean, to be honest with you, first of all, this is interpretive. It's kind of up to you how much you want to believe. Geologically, it would depend on what you're normalizing. You know, if you feel like, let's say it's a clean carbonate that is extremely consistent, you would want a really big feature filter diameter. If it was something that could potentially have more localized features, then I totally agree with you. You would want to go with a smaller feature filter diameter. In the case of this specific example, I played around with something smaller like the 10 or 20. And when you normalize with that, or when you zoom in on those wells, you can see that the wells that are causing that anomaly are in fact erroneous wells. So yeah, I agree. It's something that you need to kind of look at as you go along.
Okay, so still be the interpreter in that sense.
Exactly. Yes.
Okay, so we have a question from Vaca. Can you comment on log environmental corrections like bad conditions, washouts, etc.?
I mean, yes, I can. They are definitely necessary. Log normalization can sometimes kind of do a pseudo accommodation for those. But oftentimes, I mean, if you want 100% petrophysical solution, you should try and find the DLIST file and do the original environmental corrections. But in general, log normalization can accommodate for some of those issues. You know, if there's a washout, you may be out of luck. And that's another thing you need to take into consideration. I tend to prefer, if I'm doing any petrophysics, any normalization, I'll eliminate any log data that looks to be washed out. I don't want that going into my calculations at all. But yeah, that's something you'd have to take into consideration.
Okay. Another one from Thomas Martin. Other curves would you recommend this workflow on, or is this only useful for gamma ray? You
know, I think you can do it on any curve. It gets risky trying to use it on resistivity because the mechanics behind that are not very straightforward. I tend to do it typically on gamma ray. Neutron definitely needs it. This is really nice with neutron because oftentimes in some basins you'll have logs that are on a limestone versus sandstone matrix, and if you don't catch all those in the beginning, this will often accommodate for those. Doing it on row B, I've found there are three things that you don't talk about in the workplace, and that is religion, politics, and normalizing row B. It's a very polarizing subject. I like to do it, but when you do it, you need to be extremely careful because it could be pretty bad. So again, mainly the porosity logs and the gamma ray is what I tend to use it on, and I'm more careful when I do it on the porosity logs. Yes. Okay.
Yeah. So we have from RSM, generating trend surfaces work better than using a filter or a feature filter?
Yeah, I believe, let me actually zoom back one. I think in this example, I mean, I applied a feature filter diameter, but when I did this spacing, yeah, I mean, you need to look at what your software is using. And I think in some cases, doing it one gridding method versus another would work better depending on what you're looking at. I prefer to try a few different methods, a trend surface, a feature filter, and see what the maps look like, and then make the decision there. It all depends on what your data looks like, how spread out it is, how variable it is. So again, like a lot of this example, it's not one size fits all. There are different types of gridding algorithms you can use, and you kind of need to just decide which one works best with your specific data. Hope that answers it.
Well, good. Well, Mark, it looks like that's our questions for today. I want to thank you again very, very much for being willing to present to us.
My 8-year-old, his favorite joke about the violin is, you know, what's the difference between a violin and a fiddle? Now, you got to understand, this is an 8-year-old telling a joke, but I guess now it's a dad telling a joke. The difference between a violin and a fiddle is a violin has strings and the fiddle has strings. Oh, I just heard a laugh from downstairs. So